In this sequence of videos, we're going to talk about reinforcement learning, which is kind of a continuation of this idea of how do we make decisions in an online setting, right? Where we make decisions, we get some feedback, and we have to adapt. The difference here is we're making decisions, and then as we make a decision, our place in the world, in our environment kind of changes, or the world or environment changes around us. And we get some information, right? Was that a good decision? Was that a bad decision? We get some reward. And then, we kind of make another decision, maybe things change more. And we have to learn how to kind of navigate the world in a sequence of steps, a sequence of decisions to maximize our reward. And so one common application for this way of thinking about problems is robotics, right? You have a robot moving through the world, trying to understand what are the different places it can be, what is the environment, what is its goal. And so we'll talk about how you formulate a problem, define like what is the reward you get for doing certain things, what are the different states, what are the different actions you can take. And then we'll talk about a few algorithms for trying to figure out what is the optimal policy. And a policy is just a way of thinking about, okay, if this is the state of like where I am, where the world is, what's the best action I should take? And we'll kind of formulate a few different ways of thinking about that. So how does this reinforcement learning stuff kind of fit in what we've already learned, like about bandits and all of that? Well, so in the bandit setting, remember we have multi-arm bandits where, you pull an arm on this multi-arm bandit and you get a reward, right? You pull an arm and you get a reward, you pull a different arm, you get a different reward. And each arm has its reward distribution. And remember that the individual rewards that we get, we assume that they were IID, right? And that each time I pull an arm, I get a draw from some distribution that corresponds to that arm. And that draw doesn't really depend on like whether it's the first time I'm pulling it, the second time I'm pulling it, like what I've pulled before. It just depends on which arm I pull. And so this is kind of a simplifying assumption that helped us do a lot of interesting analysis about, okay, what's the best arm? What's the best policy? How do we find the best arm? We talked about the UCB, Thompson sampling algorithms. But in the reinforcement learning setting, we're going to say, well, what if it's not just, I pull an arm and it's IID? What if when I take an action, then the state of the world changes? And it's not just, the same arms with the same distribution, it's things change. And as usual, when we take a step beyond assuming things are IID, we're going to take the simplest possible extension that we can and say that things are Markov. And remember, Markov is just this general term, based on Andrei Markov, this general term for when we assume that things aren't IID, but that what happens at this time only depends at what happened at the previous time, right? Kind of like with Markov chains where, what state you're in now only depends on what state you were in the time before. And similarly only affects what state you'll be at the next time. And to go 2 time steps from now, you just have to look at where you are at the next time step. And we'll formulate something called a Markov decision process that captures this idea exactly. So again, bandits, everything's kind of IID. We talked about this idea of contextual bandits where maybe you have some context for things and maybe things depend on something but if things are changing and evolving over time, that's where reinforcement learning comes in, where we want to kind of adapt and learn what are the different states of the world, what's going on, what's the best thing to do, not just in general, but in each particular state. So when you talk about reinforcement learning, we're going to use this framework of Markov decision processes. And this is just a way of formulating the problem so it's really clear like what we're trying to solve, what information we have, and what we're trying to figure out. So what is the Markov decision process? Again, remember, we're trying to model this idea of some agent moving through the world and like through an environment, trying to like accomplish some goal or some task or trying to like do something. And what we say is that this agent, we're usually going to call it an agent, this agent moves through a bunch of different states, right? There's different states that the agent can be in. I can be here, then I can be here, then I can be here. And in each state, I can take an action, right? You can imagine a robot can maybe, a robot that's trying to fold clothes. One action it can take is to like reach down, like move its arms down or grab the shirt or, lift one arm up over the other. And we'll talk about this example on the right of the slide here in a sec. We also have a transition function, which says, okay, if I'm in a particular state and I take some action, then what are the other states I could end up in? And so for each state S that I'm in now, and each action A that I take, what is the probability of ending up in state S prime? And so we'll kind of explore what this means in a little more detail in this grid world example. We also have a reward function, which says, okay, if I make a particular transition, right? If I start in state S, I take action A, and then I end up in state S prime, what's the reward I get? How good was that transition, right? If that reward was really good, then it should be high. If it was not a good transition, it should be low. A lot of times we'll just have this sort of baseline where it only depends on the current state or the next state. It's just kind of the same regardless of the transition. It really only depends on the state. In most formulations, we'll do this, but in general, we can have it be any. We also have like a start state. Where does the agent start? And maybe some states are like terminal states, right? In those cases, the game ends. And we're going to be working a lot with this grid world example, right? So if you look at this little kind of like game on the right, you have this robot, right, which is in the square kind of near the bottom right. And this robot is moving around through this grid, right? And so the states in this case are the individual squares on the grid, right? You can see that there's a bunch of different squares corresponding to different states. Some of them are reachable, some of them are not. You can see that, for example, this state over here is not reachable. And it seems like, either this is the start state or maybe, in this case, this is the start state. So the robot starts in some state and its goal is to get this diamond. And when it reaches the diamond, it gets a reward of +1 and the process ends. On the other hand, if it falls into this pit over here, it receives a reward of -1 and the game ends. So obviously, you can imagine that the robot kind of wants to make its way up here and get the diamond and doesn't want to fall into the pit. And so why is this transition function probabilistic? Well, let's say that this robot's motor doesn't really work that well. And so when the robot tries to go in any particular direction, maybe there's an 80% chance it'll actually go in that direction, but then a 10% chance it'll like end up in one side and 10% chance it'll end up in the other side. So you can imagine in the robot's current state over here, if it tries to move up, right? So what are the possible actions for this robot? Well, it can go up, it can go right, it can go left, and it can go down. And those are the kind of the same actions regardless of what state you're in. In general, some states may not have certain actions available to you. But if you try to go up, the transition, t of this state and up, if S prime is this state over here, then it's 0.8. If S prime is this, then it's 0.1. If S prime is this, then it's 0.1, right? And for all the others, S prime, the t transition probability is 0, right? So you can imagine this kind of defines, okay, if I'm in a particular state, here and I take a particular action, where might I end up? And this kind of captures the uncertainty. And what's the reward? Well, the reward for these two terminal states is listed on the states themselves. But for other states, well, we want to kind of encourage, in this particular case, we wanted to encourage the robot to kind of like reach its goal quickly, right? You can imagine if we just set the reward to be 0 for all the other states, then the robot could just kind of dawdle going back and forth between these two states forever. And then it would maybe eventually reach its way here and do nothing. So what we want to do in this case is we want to make the reward for every state negative to encourage the robot to reach its goal faster. Now, I just said it's negative, but like, should it be like -0.1? Should it be -2? Well, we'll kind of see what happens if we choose different values in a moment. So this is the grid world example, right? We have the robot, the states of the different squares it can occupy. The actions are up, down, left, right, what it can take. The transition function, which says, if you move in a particular direction, what are the probabilities of where you can end up? And we said it's like, where you can go 0.8 and then like the other side's 0.1. And we have a reward function, which we said for these two is, +1, -1. And for all the other states, it's going to be like negative something. We'll see what. And a start state, which in this case, maybe it's the bottom left, and a terminal state, right? There's two terminal states in this case, these the diamond and the pit. Okay, so now we'll talk about if we have a Markov decision process, how do we actually like figure out what the robot should do? Okay, so when we set up a Markov decision process, what are we actually trying to get? Well, what we really want is a policy. And a policy is just a fancy way of saying we want something kind of like the map shown on the right here. Right? We want to know for every state, what's like the best action I can take? And best means what'll give me the highest reward accumulated over time. right? What'll give me the best reward now, plus like the next step, plus the next step, plus the next step, plus the next step, right? So if I sort of add up all my rewards from now until the end of the process, which policy, which set of actions for every state will give me the highest sum of rewards. And so it's sort of like a mapping. It says for every state, this is the action you should take to maximize your reward. And we can see that, if we set the reward, the baseline reward for the particular states a particular way, then we get this very intuitive policy, right? At every step, we kind of want to make our way to the diamond and avoid falling into the pit, right? And so we want a map like this, right? A policy that says, okay, for every state, what's the best thing to do to maximize my sum of rewards? And let's look at an example of what happens if we kind of like tweak the rewards and see what policies we end up with. So if I set so here's 4 different policies for 4 different baseline rewards. And remember, what is this like baseline reward thing? It says for every state, not counting the goal states, what is the reward for just like entering that state, right? Or sort of exiting, being in that state. And so if the reward for being in a particular state is negative 0.01, we end up with this policy. Negative 0.03, we end up with this one. Negative 0.4, we end up with this one. Negative 2, we end up with this one. So let's start with this one on the bottom left. It's kind of the easiest to understand, and then we'll kind of like look at the others from there. So what does this one say? Well, it says in general, make your way in any square you're in, kind of make your way towards the diamond, right? The +1 square with the diamond in it. And notice here in the bottom left where you think, oh, maybe there's a tie, but actually there's no tie here, right? It says the best thing to do is actually to go up. Why is the best thing to do to go up here? It's because the top path is a lot safer than the bottom path. Remember that this robot has, the motor's not perfect, right? If I make it a particular, try to go in a particular direction, there's a 10% chance I might like accidentally go to this side or accidentally go to that side. And so in particular, if I look at this state over here, if I try to go up, there's a 10% chance I'll just sort of try to go this way and bump into the wall, stay in the same spot. But there's a 10% chance that I might go right and end up in the pit, right? So that's kind of bad. So this state is like, it's good because I'm close to the goal, but it's not as good as this one, right? Both of these, both this square and this square are sort of 2 away from the diamond, but this one's better because it's a lot safer. Right over here, I don't have any chance of falling into the pit. So this is kind of the policy we'd expect. What if we look at this one over here, right? So what is the difference? Over here, our reward for every state is negative 0.4. So that means that for every kind of time step that we spend moving around, we lose 0.4 reward compared to the +1 that we get if we kind of win and hit the diamond. Now over here, this says, well, the reward for just kind of like moving around is only negative 0.01. So it's really, really small, right? So if we just kind of like move around a lot, yeah, you like lose a little bit every time step, but it's not that much. So, you are kind of encouraged to go to the goal, but this policy encourages us to be really cautious. It kind of favors safety over speed. In particular, let's look at what's going on in this square over here, right? In the policy we just looked at, the best move to do is actually to go up, right? Which is sort of intuitive, makes sense. If you're here, you want to get to the diamond, you go up and then over. But here, the best thing to do is not to go up, but actually to try to go left. Why is the best thing to do to try to go left? Well, it's because if you try to go left and you end up, or you try to go left and you end up, bumping into the wall, there's an 80% chance you'll bump into the wall and won't move, but there's a 10% chance you'll go up and a 10% chance you'll go down. But there's a 0% chance that you'll end up falling into the pit, right? So this says, okay, don't even risk falling into the pit. Just try to like move away and just hope for that 10% chance that you move up, right? So this, you may end up spending a long time just trying to like, just like boom, boom, just like moving into the wall and not really getting anywhere. But eventually, hopefully you'll make it up at some point. Now over here, we can see that this is kind of in between, where we can see, okay, if you're 2 steps away from the goal, like here, then yeah, go up. But if you're over here, then actually just like take the long way around. If you're over here, instead of trying to go up, up, and over, take the long way around because it's safer. right? So there's this kind of trade-off as we increase the penalty on, just sort of the reward we get for being in a state. There's this kind of trade-off we get between safety and speed from around these three. Now, let's take a look at this one where the reward for being in a state is negative 0.2. Now, what's going on here? So if we're in this state down here, the optimal action is actually to go directly into the pit. Why? It's because if we take our time to go all the way around and go here, 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 then it's like -2, -4, -6, -8. And then we get the +1, our total reward is -7. Whereas if we just like jump right into the pit, then our reward only is -3, right? So it ends up being better to just like go into the pit quickly, end the game as fast as possible, rather than even trying to get the reward. Because the benefit of getting the reward is only +1, but the cost of moving around is so expensive. So, and that's even true over here, where even if you're 2 steps away from the goal, it's still better to just try to go into the pit, because that still only gives you a reward of -1, as opposed to going over here where you pay an extra cost of -2 just to move through the square to get to the goal. And that doesn't outweigh the benefit you get from the difference between these two. Okay, so this kind of shows that you kind of have to tune your reward depending on your situation. If you're in this grid world example, it makes more sense to have a negative reward. You may end up being in a situation where your base reward should be positive. If your sort of agent is just trying to like survive, or just trying to just moving around and doing nothing is actually good. This really depends on the setting. There's a trade-off here. What it is, where to go on it depends on your use case. Okay, so this is sort of some examples that I've shown you. But next we'll talk about how do we actually figure these out? How do we actually figure out what the best policy is and where to go, right? In this case, I just showed you these and it seems like, okay, these make sense. In the next couple of videos, we'll talk about how we actually figure out the best policy. All right, so in this video, we're going to talk about how we actually figure out what the optimal policy is. And so as a reminder, remember we have this T function, which tells us like what's the probability of ending up in state S prime if you start an S and take action A. And we have R SA S prime, which is the reward for going from S to S prime by taking action A, right? So I'm using green for states and purple for actions. Okay, so these are kind of like the setup for the problem, and I'm going to define a few quantities. The first is going to be this thing called V star. So V star is something that is a function of a state, and it's going to kind of measure how good is a particular state, right? Some states are good because they kind of like lead to more rewards. Other states are not as good because they lead to fewer rewards. So V star is going to be defined, and like, well, how do I measure goodness? It's the total reward. It's the total sum of rewards if we start in state S and act optimally, right? And so V star is just kind of defined as like, how good is the state? And the goodness is measured by the sum of the rewards if we start there and act optimally from there. Okay, and what does like act optimally mean? Well, we have to define our policy, right? So we have our policy, which we're going to use the letter pi for. This is not 3.14, this is just pi as in the policy. And so pi is a function of a state. And this is the best action for state S. Okay, and so we have V, we have pi, V star, we have pi, and okay, but V star is kind of nice because it tells us how good a state is, but it's not good for helping us determine a policy, which is what we really want. Why do we want a policy? It's because that's what's going to actually tell us in a particular state, what do we do? Like, what decision do we make? What action do we take? And so if we're going to try to figure out what the best action is, we need to have something that is not just a function of the state, but is like a function of the state and the action, right? It's like, how good is this action from the state? And so that's where we're going to define Q. So Q is a function of a state and an action. And it's the sum of rewards if it's just like V star, except it's like more specific. It's like talking about that specific action. We take action A. If we take A from state S and then act optimally. Okay, so these are kind of like defined in terms of the optimal actions. They're kind of useful quantities, and we'll end up actually defining recursions in terms of these. So you can imagine that, like, you can see that, well, V star is like, well, it's the, it's sort of related. These are all kind of related to each other, and they're also related to each other kind of like one step down the line, right? You can imagine that Q is like the sum of rewards if we take A from S and then act optimally, right? So also, these are all kind of the one thing that I'm missing here in these definitions is that these are the expected sum of rewards, right? Because remember, this whole thing is random, right? Our transition probabilities are random. Sometimes, we end up in one place. Sometimes, we may end up in another. So we need to take expectations over all of these. And so in the next video, we'll define recursions over these quantities to help us understand what's going on. All right, so now we have these quantities like defined in terms of what they are. How do we actually figure out how to compute them, right? So like, how do we define these mathematically? Well, we'll end up defining them recursively in terms of each other. And then we'll see how we can kind of like be really clever about how we compute them to figure out an optimal policy. Okay, so what is V star? V star is the sum of rewards if we start in state S and act optimally. Well, acting optimally means we like choose the action, the best action from there. What is the best action? The best action is the one that maximizes the sum of rewards from there, right? So it's sort of like the sum of rewards if we take the best action and then act optimally. But that's precisely the definition of Q, right, for the best action. So to make that a little more concrete, we can say V star of a particular state is, what we're going to do is we're going to look at the Q function for that particular state, and we're going to look at all the actions we can take. And for each of those actions, we're going to like look at what the Q function is and then take the max. So this is like the max over A of the Q values for all that, right? So essentially that's saying the value, like the goodness of a state, is the max over all possible actions you can take from that state of the Q function for that state, right? And again, remember, Q function just says like, what is the goodness of being in a state and taking an action? All right, so that's maybe that's useful, but it's only useful if we can define what Q is. So how do we define Q? Well, the Q function for a particular state and taking an action from that state is, it's the expected reward if we take that action and then act optimally from there, right? So it's the expected reward. And so how do we take this? What is this? What is expected reward? It's an expected reward because remember that the transitions are random, right? There's some randomness. We might end up in one state, we might end up in another. And so what we're going to do, how do we take an expectation? We just sum over all possible states. And each one we're going to weight by how likely it is. Well, how do we know like how likely each state is? That's exactly what T, the transition probabilities are, right? So this is T SAS prime. And so this is like the, how likely that particular S prime is. And then we have to take what's the reward for making that transition, right? So this is like, okay, this is the probability. And then what's the actual reward? Well, the reward for this is the reward for making that particular transition plus the future rewards that we'll expect to see, right? So it's the reward for making the transition from S to S prime by A plus the like future like best possible rewards that we'll get. Well, how do we measure like what's the like, right? I don't want to like write, well, that's going to be like another sum, but that's really just V, right? If we're in S prime, we can measure like the goodness of being in S prime using V star of S prime. Of S prime, right? And now we're almost done, right? And why is it almost? It's almost done because we actually need one other factor in here, which is to say that we do something called reward discounting, where we say like getting the reward now is better than getting it in the future, right? Again, if we want to encourage like, obtain more rewards now, getting things in the future is not as good to kind of encourage our agent to act quickly. Then we can include a discount factor, which says if you get a reward like 1 step from now, it gets multiplied by some number gamma, where gamma is like maybe like 0.9 or something. 2 steps from now, it gets multiplied by gamma squared. 3 steps from now by gamma cubed. And so what we're going to do is we're just going to throw this in here. So this here is our discount factor. And so to summarize what we have here, this is the probability of ending up. This is the probability of getting to S prime. And this is the reward from S prime plus the transition, right? Or in the other, it's the reward from like the transition to S prime plus like what rewards can I expect in the future from being in S prime, right? The first term is just like the reward for making that transition. Second term is like, what are all the rewards I'm going to get in the future, right? So we have this recursive definition that's really just like a fancy way of writing out an expectation, where we have V star defined in terms of Q, Q defined in terms of V star. Okay, and so now in the next couple of videos, we'll talk about how we actually kind of solve this recursion really efficiently. And we'll see we can use some similar tricks to what we did when we learned about backpropagation. All right, so let's think about now how we'll actually compute these functions V. So we'll start off by talking about how we compute V, and then this is called value iteration, where we figure out like what's the best value for each state. And then next we'll talk about something where if we don't know the transition probabilities, then how do we estimate the Qs using something called Q learning? Okay, so for now, let's talk about value iteration. How do we figure out these Vs? Well, what is the definition of V? It's just this, right? It's like, what is the max over A? Q, and Q is just the expected reward here, right? And remember the reward was like the reward for making that transition plus the future rewards that we'll get from that state. And we weight each one by the probability of that, summing across all possible like future states from that action. So I could like really just plug this in over here, right? I can like take this whole thing and plug it in here, and then I get a recursion for V star of S in terms of V star of S prime. But I end up with a problem there, which is that then V star is defined in terms of itself, right? You can imagine like, what if I have a setup where like, if I'm in a particular state and one of the transitions from that state is actually to end up in the same place, right? Like if in the grid world example, remember like if a robot tries to like move against a wall, doesn't move and ends up in the same spot, then I'll have like V star of S and on both the right-hand side and the left-hand side. And how do I do that? And so what we're going to do to avoid that problem is we're just going to introduce time into the equation, right? So we'll say, okay, what is V star of S at time t? We'll start with time t equals 0, then like, then we'll have time t equals 1. And that way we have like the value of being in state S at time 0, then the value of being in state S at time 1, and so on. And we'll just go from t equals 0 all the way up to some like big number t, capital T. Okay, so let's think about how we might write some code for this. So we have some set of states, right? We define a bunch of states, we define a bunch of actions, and we define this discount factor gamma, right? This is like the Greek letter gamma. And then we have some function defined t, which is our transition probability. And then we have some reward function defined. I'm not going to bother writing these out. They depend on your problem. And now what we want to do is we want to compute what V is. right? So remember v is like the value function. I'm not writing the star. This is like v, the value function for a particular state s at a particular time t. And so the way we'll do this is we'll say, well, if we'll start off by saying if t is less than t, so we'll have this t equals, I don't know, some like relatively big number, max time, then what do? Well, we're going to take a max over all the actions, right? So we'll kind of like end up looping over all the actions. So for A in actions, we're going to compute some stuff, and Q equals stuff, and then we'll just do the value equals max of Q, and then best so far. And we'll start off by initializing best so far to negative infinity, right? So we start off with like, the best so far, and we're just taking a max over all these, right? So far, what have I implemented here? I've implemented just this max. Now, what does the actual computation of Q look like? It's this sum, right? So I need to do a sum, and I'm going to sum over all possible new states. So I need to actually do a Q, initialize it to 0, and I need to actually loop over all possible new states. And for each new state, I'm going to compute, what am I going to compute? I'm going to scroll back up here. I'm going to compute the transition probability and multiply that by this. Great. So I do T of S, A, S new, right? This is my transition probability. I multiply that by the reward for taking that transition. That's this R function that I defined, S, A, S new. And I'm going to add gamma times the value of that new state at time t plus 1. And this is my Q plus equals this. So this is, just to get this to fit all in one line, fit on the screen, I'll do this, right? So basically I'm looping over all the states, and for each one I'm adding up what is the probability multiplied by the reward for that transition plus the future rewards. Okay, so now I have a recursion, and then if I'm doing a recursion, so I've done this to define Q. And this tells me, okay, for that particular action, what is the Q for that being in this state and taking that action. And then I take the max over all possible actions. Okay, so this is my value iteration. And I need to do, otherwise, if we're at the max time, then I just return 0. And in here, I need to make sure to return value. Great. So now I've defined this recursive function where, every time I make this recursive call, t is always increasing. And so I'm always going to make my way towards the base case where t is at its max value. Now, there's a problem with this. And the problem with this is that this is going to end up doing a bunch of redundant computation, right? You can imagine if I have like 2 different ways to reach a particular state, right? In the grid world example, like if I start off in like the bottom left corner, and then kind of like there's multiple ways to like reach a different state, this is going to have to do that redundant computation multiple times, right? So this recursive computation is going to have to repeat itself multiple times, kind of a pain, and it's going to be very costly, especially if my state space is large, where I'm going to have to repeat this computation many, many times. And we kind of saw something similar when we learned about backpropagation, right? Where we said, well, this didn't really, we kind of like structured the computation in a way that like led to some redundancy. So is there a way to do it more efficiently? Well, doing it this way, we start at t equals 0 and kind of like, just kind of like say, okay, like add in what's the next thing. But it turns out that if we start at t equals t and work our way backwards, we can actually do things a lot more efficiently. And so that's what we'll do in the next video. All right, so we've seen that this first version is pretty slow. Why? Because it just keeps making these calls to v of s mu t plus 1, right? And we see that you might end up calling the same function multiple times and have repeated work, right? Where it's sort of like you call it, it needs to compute it, then somewhere else also needs v for that state, and then it has to repeat the work over and over. So can we do this in a more efficient way, right? Can we do the same like math, but structure the computation in a way that it's more efficient? And we'll use the same kind of idea that we used in backpropagation, which is this thing called dynamic programming. And how does it work? Well, we're just going to say, well, this way we started at the beginning, right? You can imagine we kind of like start with t equals 0. And then we kind of like each time we went down, we kind of like went up t equals 1, then like t plus 1, t plus 1, t plus 1, t plus 1, and so on. But if we start at the end and work our way backwards, it'll actually be a lot faster. And so what we're going to do is we're going to have this array of the v values, and I'm just going to have this be a bunch of zeros, 1 for each state, and we're going to need an array that has like basically 1 row for each state and 1 column for time, right? So the first column has like everything for time t equals 0, then for time t equals 1, time t equals 2, and so on. And we're going to kind of like work our way backwards and start by filling in at the end, and then say, okay, the end, just the, at t equals infinity, it's 0. And then we'll kind of just work our way and fill in all the way to get to t equals 0. And that's what we have. Okay, so this is just going to be t. Now, what we're going to do is we're going to loop. And so I said if we're going to start at the end where t equals, start with t equals capital T, then we're going to have to do a loop. And we're going to have to loop where we start at t and go down to 0, taking steps in size -1. Right? And remember, we end at -1 because we need to, end it where 1 passed where we're actually ending. Okay, so we have t equals t in range t -1, -1. So we'll start at t, work our way back to 0. And what we're going to do is we're just going to loop over all the states and just fill in each one at each iteration. So we're going to loop over all the states and fill in the v array of s comma t equals something. How are we going to fill it in? Well, remember, to figure out the value at that particular state, we need to loop over all the actions, and then within each action, we need to loop over all the possible new states, right? We're doing, again, this like max of the sum thing that we did before. If I scroll back up to the equation, right, we have this essentially, we're taking the max of the sum, right? Max of q, where q is a sum. So we're taking the max over all actions and the sum over all possible states. And the sum is basically like a weighted combination of the rewards, where each the weights are the t's. And then the max is just like pick the reward from the best action. Okay, so what does this look like? It looks like for t in range t for s in states. So we're going to have to do a loop over all the actions, and we're going to have to do a loop over all the new states. Great. And this loop over the actions is going to be a max. So, as I do with the max, I start off with the best so far. And then the loop over actions is going to be a sum, right? So I start with this value is 0, and I'm going to have to do some adding into stuff. And then after I take all the actions, as I take each action, I'm going to say best so far equals max of best so far and the q, right? So this thing is like the q of a particular state and a particular action. And I'm adding in, all the different possible things for each of the new states. And then I'm just saying for each of the actions, what's the best over all of them. And what am I adding? It's exactly the same thing that I added up here, right? So I can even just copy paste, almost copy paste this here. The only difference here is that instead of calling this function recursively, I'm just going to look at my array, and I'm going to look at the array for the new state at time t plus 1, right? So actually, that means I need to start at t minus 1, right? So I start and at time t equals t, then everything's 0. Then I'm going to fill in at time t minus capital T minus 1, where I'm just going to look forward and all those values are going to be zeros. And then I'm going to have some nice values filled in at capital T minus 1, then work my way backwards from there. And so now with the array, all I do is I need to just fill in the best so far. And this is my faster version of value iteration. Why is this faster? Is because it only needs to run this whole kind of like looping over the state, action, new state once, instead of this, which may call it multiple times. And again, this is just another example of dynamic programming. And this is kind of a well-studied thing in reinforcement learning. These are called the Bellman equations for value iteration. All right, so now we're going to talk about how we adapt the process we just did to the case where we don't actually know T, right? We don't know the transition probabilities. We don't kind of have as good an understanding of what the lay of the land is, like when we take certain actions, what ends up happening. Instead, we're going to have to try to estimate, like what's going on from basically just a bunch of observations. And so what the data we get then is going to be a bunch of trajectories. And what is a trajectory? Well, each trajectory is just going to be, we were in state S0, we took action A0, and, we got some reward, R0. Then we were, in state S1, we took action A1, and we ended up with a reward R1. And so on, right? S2, A2, we got R2, and so on. And then, that's one trajectory that happened. And then let's say we try it again, and we get some different sequence. And we try it again, and we get some different sequence. And so we have a whole bunch of these trajectories, right? Where each one kind of represents one iteration of us making our way through this unknown world where we record what happens each time. And now how are we going to use this to learn the optimal queue? And so this process is called queue learning. And the idea is very simple. We do something pretty similar to what we did before, except now we have this idea, well, we don't actually know where things are. So we're going to be a little more cautious in our updates. So before in the example we did before, we kind of learned how, okay, we can have this array of V's, and this array of the V's has what our estimate is for the value of each state. You can imagine extending that to, instead of just saving the V's, you also save the Q's. And we'll actually do that in discussion, where you don't just save what the values are, you also save the Q's. And we can kind of extend that idea to this. And so Q tells us for every state and for every action within that state, what is the best, what is the sum of rewards I'm going to get if I take that action from that state. And so Q is a function that takes in, its first argument is a state, and its second argument is an action. So you can imagine then, think of like an array, right? Where you have your Q as an array where on each row corresponds to one state, each column corresponds to an action. And each entry in the array tells you how good is that action from that state. Now, we'll call that array Q hat, and we'll just initialize it to something. And what we're going to do is we're going to repeat the following process for each of these sort of like tuples in our trajectory, right? This is like a tuple, this is a tuple, and so on. And how is this tuple going to work? How is this process going to work? Well, we're just going to say that Q hat of, and so the algorithm is, we just repeat the following process. We say Q hat for state ST, AT, right? Where first like T equals 0, then T equals 1, and so on, is going to be assigned to something I'll tell you about later, plus the term that's very intuitive, which is we're just going to say it's the reward, right? It's like how good was that Q? Well, it's the reward plus plus exactly what we did before, right? It's sort of like gamma times the max over all these actions, Q hat of st plus 1, comma, a prime, right? So essentially what we're doing is we say, okay, at this particular, like for this particular tuple, right? If I took action AT from state ST, then I look at what was ST plus one, right? Because I remember I observed the whole trajectory and I say, okay, where did we go from there? And where we went from there, we say, okay, let's look at all of the, like in my queue, which kind of like has the information I have so far. Let's like look over all the actions that I could have taken from there, use that as my estimate for that queue, right? And so this is like my estimate for V plus one, right? This is my estimate for VT plus one, multiply that by my discount factor. And this is my update, right? Kind of makes sense that this would be my, that this would be my update for Q, because this is exactly the definition, right? This is the definition, except, you know, I'm, instead of weighting this by the probability, which I don't know, I'm just repeating this many times. And so in expectation, I'm going to observe, you know, if I observe certain transitions more, then they're going to get added in more often. If I observe other transitions less, they're going to get added in less often. So in expectation, this is going to kind of average out to what we have before. Now, the problem with this is that this isn't quite, you know, this is sort of just saying, if we do just what I have here, it's going to say, well, you know, then just like blow away whatever you had before with this one particular sample, right? Because each of these you can kind of think of as like a single sample from like the possible states and transitions and actions and all that. So what we're going to do instead is I'm going to say, I'm going to kind of weight this, where my weights are going to be, this is going to be 1 minus alpha times the existing value plus alpha times this. And this is the equation for Q learning. Very straightforward. All we're doing is we're saying, okay, you update Q hat with to be some like weight. Alpha is a number between 0 and 1. You say like, well, it's like kind of like what it was before, you know, like don't like just completely blow it away. It's like kind of like what it was before, but it's also kind of like this reward, right? This like what I observed plus like what I think it is for all the other states, right? So this is sort of an algorithm to say, well, let's approximate the Q function if I don't know the transition probabilities. And you can imagine alpha is kind of like a parameter that very similar to your learning rate in stochastic gradient descent, right? You can imagine that the bigger values of alpha, like alpha is closer to 1, means that you just like completely blow away what you have every time with this new estimate from this one sample. Whereas values of alpha close to 0 means like you're very cautious. You say like, well, it's mostly like what I think it is, but maybe you'll like add in a little bit of new information from this new thing. And so there's a lot of like theoretical analysis of this that shows that it turns out things converge if over time you slowly decrease alpha and have it trend towards 0. And if you do that, then this algorithm will converge. And this is a really powerful idea, this idea of Q learning. And you know, the example I've talked about, Q is just a simple array, but it turns out that you can actually use this to learn more complicated Q functions. People do this a lot. You know, if you've heard about things like AlphaGo, all these AIs that play games, they use reinforcement learning. They actually use Q learning, but their Q hat is not just an array, it's a deep neural network. So we can actually use any Q hat here, where you just kind of like do an update where you say, wait a little by what we had before, but also update it with this new information from this new sample from this trajectory. And you'll get some practice trying this out in lab. All right, so in this sequence of videos, we talked about reinforcement learning. And what did we learn? Well, we had this setup with this Markov decision process. We have a bunch of states, we have a bunch of actions. We're kind of like, you know, an agent moving around, taking actions in the world, moving from state to state. There's some transition probabilities where if you're in a state and you take an action, it's kind of random where you end up. There's rewards, right? Taking a particular action from a state and ending up in another state gives you a certain reward. Some transitions are better than others. Sometimes you end up in terminal states with, you know, usually positive or negative rewards. And we talked about this like idea of value iteration, right? Where we have this value at each state. where we can kind of like, we had this fancy algorithm, like the Bellman equations, where we did this computation structured in an efficient way to compute the value for every state if we know what the transition probabilities are. Then we went to the more realistic setting where we don't know what the transition probabilities are, right? And then we talked about Q-learning. And what was Q-learning? We said, well, let's like have some idea of the Q function. Remember, what was the Q function? It's like from a particular state, taking a particular action, how good is it? How good is it meaning, like, what's the sum of rewards I can expect from there if I take this action from the state in the future? And we said, okay, let's like learn what that is. We initialize it to some value. We thought, it's like an array where for every state, for every action, here's like how good I think it is. And we observe a bunch of trajectories, right? We observe like, aha, if I have like, this sequence of states, actions, rewards, then I keep updating my my queue, my array with like, okay, based on these states, these actions, these rewards, I update in this way. And we saw that, that kind of works out well, and you'll get more practice on this in the lab as well. Okay, so again, that's reinforcement learning. It's a way of kind of reasoning, making decisions in a world where there's uncertainty, there's like the environment reacts to where you are. That's kind of a whirlwind tour. There's obviously a lot more depth to the topic, but this is kind of the, kind of whirlwind tour with all the big ideas that we've covered in this class.